All right, E&M 2012, number 2. This gives us a voltmeter, or I suppose this actually is an ohmmeter, and a strip of paper that can conduct electricity a little bit. And so what this experiment is that we're going to fix one end of the ohmmeter and then move the other one to different lengths along the strip of paper. So the length of the resistor is getting longer, and then we're going to measure the resistance. And they tell us the thickness, and they tell us the width, and then we're going to have the length. So we can figure out the cross-sectional area and the length of the resistor, and we're going to graph this. So let's see if they tell us plot a linear graph from which the resistivity can be determined. So they're not giving us a whole lot of instruction here. Now on the equation sheet, there is the formula relating the resistance to the resistivity, length, and cross-sectional area. Now because this is rectangular, this will be length and then width times depth. We'll call that depth, or height if you prefer. Let's see, they called it thickness. So let's call it thickness. So width and thickness. Width and thickness. That'll be confusing because I'm used to having that for time, but we can use T for thickness here. So if we want to be able to get the resistivity, and R and L are our variables, so that means R is going to be, let's make that Y, and then our slope will be resistivity, thickness, and width, and then length will be our X variable, and they've given us these two things. Nice, so let's say length, and they've measured it in meters, and resistance, that guy is, you know what, let's make that kiloohms. Kilo ohms there. So now instead of 80,000, we'll just have 80, 180, 260, 370, and 440. Just have to remember that K is there when we come down here to find the slope. And we're going to need our scale. Let's do 0.02, 0.04, 0.06, 0.08, 0.1. That'll get everybody going across. And then this will be 100, 200, 300, 400, 500. Yeah, that'll work. 100, 200, 300, 400, 500. So we're going to go over to 0.2 and up to 80. Over to 0.4 and up to 180. Over to 0.6 and up to 260. 0.8 and 370 will be, let's see here, it's in between. I know I'm being a little bit sloppy here. And 440. And hey, look at that, we've got a straight line just like they told us we would. Now we need to draw the line and find the slope. I'm going to pause while I draw the line. I've got my line, and now we need to choose 2 points. Well, we finished part A. Have our scale, have our labels, plotted our points, drew a straight line that best represents the data. Now for part B, using the graph, which means not using the data table, using the graph, let's get the resistivity. So for part B, slope is going to be the resistivity over the width times the thickness, which they gave us up here. And that will be change in Y over change in X. So what we need to do is choose suitable Y's and X's. Fortunately, 0, 0 is on the graph. And then we have here, that point looks pretty good. Ooh, this point looks a little bit better. Keep in mind, this is a hand-drawn graph, so there has to be a fair amount of leeway for what the actual slope and therefore what the actual resistivity is going to be. So for our slope, this looks like 400 20, 40, 60, 80. All right, so that'll be 480 minus 0. And then don't forget, all of that is times 1,000 because of this kilo over here. Don't forget that part. And then over the x, that will be 0.8. Let's see here. 84, 88, 92, 96, 1. Yeah, so each one is 0.004, which means that's 0.0104, 0.0108, and then also 0. All right, plugging these guys in, and then, ooh, don't forget that then we have to multiply by the thickness, which is 1 times 10 to the minus 4th, and then times 0.02. So that translates to 256. 2 microns. So we're going to take our answer for the slope and multiply by 2 microns. Let's see here, 480,000 divided by 0.108, and then times 2 microns. I got 8.9. Hey, that's not bad. When I did this by hand on a piece of actual graph paper, I got 9.0. So 8.9 is not bad for computer futziness. So I got rho here is 8.89. Don't forget, always give 3 significant figures, and that's going to be measured in ohms times meters. Because if you take a look up here, this guy's in ohms, that guy's in meters, that guy's in meters squared. So what we need is an extra meters on top times an ohms, and that's what rho is going to be. Now let's clear all this out and scroll down to see what parts C and D are. All right, now they tell us we're going to get these strips of paper and choose 4 and 5, and they gave us resistance values for R4 and R5. That's very convenient of them. And we're going to put in a battery, a capacitor. They give us values for that, and an open switch. All right, the time constant. All right, the time constant is going to be the resistor that's in series with the capacitor. Now these two resistors are in parallel with each other, but then they are in series with the capacitor. So the total resistance is going to be R3 and R4. Nope, R4 and R5. R4 and R5, but you add the reciprocals because they are in parallel. And don't forget to flip at the very end. So you get 201 kiloohms once they are added together. Part D. Oh wait, no, the time constant, that's the resistance. We're not done part C yet. The time constant then is going to be 201 kiloohms times 10 microfarads. So 201 times 10 to the third times 10 to the minus 6th, because that's micro, which gets us 2.01 seconds for the time constant. All right, now part D. I'm going to close the switch, voltage across the capacitor. All right, now voltage across the capacitor. When it starts out uncharged, the voltage across the capacitor is going to be 0, and it's going to slowly build up, well, slowly, over a couple of seconds, to be the voltage of the battery. So whatever the voltage of the battery is, that's going to be our limit. So voltage of the battery. And what we're going to have here is an upside down exponential decay. And that's going to be the voltage of the capacitor. Now, we also have the voltage across those two resistors. Now those two resistors are in parallel. Since they are in parallel, that means they will always have exactly the same voltage all the time. So their voltage curves are going to overlap. And they're going to start out getting the same voltage as the battery, because remember, the battery supplies the energy, the two resistors take it away, and there's nothing left over for the capacitor to deal with initially. But then that first charge gets deposited on the capacitor, and now it's going to be taking care of some of the energy, and the resistors will take care of the rest. So the graph here of the capacitor needs to be matched by the resistors so that when we add them together, we get the voltage of the battery. So these guys are going to be exponential decays. And as all of the voltage is taken care of by the capacitor over here, none is taken care of by the resistors, whereas at the beginning, all was taken care of by the resistors and none by the capacitor. And you need to note that the two voltages, R4 and R5, are the same voltage, that they're overlapping here. Also, please note that anytime you have a numerical answer, you need to have units associated with it.